Hi everyone. In today's video, we're going to use custom data, our own video, to train a nerve. Hopefully we can get a smooth output. Let's get started. For today's video, we're going to use three main resources. The first one is a notebook by Andy McSherry from Lightning AI team, where he prepared a notebook that's ready to be copied in your Lightning AI account to run VGG structure from motion. So the structure from motion is the input nerve, and this specific algorithm was developed by VGG research group. The second resource is the GitHub repository for the VGG structure from motion, and the third one is the multi-nerve repository by Google Research, where they released three nerve algorithms, but the one we're using Mip-NeRF 360, and we will use two hardware setups. The first hardware setup is the Lightning AI GPUs to get the structure from motion. Then we will move the output over to Google Cloud TPU to run NeRF, because the VGG structure from motion uses GPUs, and multi-NeRF, this specific implementation, uses JAX, which is optimized for Google TPUs. And I have a free credit on Lightning AI GPUs, and for Google Cloud TPUs, my cloud project, supported by the Cloud TPU Research, which you can contact them and just ask for a free access to TPUs. So I have a free access to GPU through Lightning AI credit, and I have free access to TPU through Google TPU Research Cloud. So let's get started with the video first. I'll show you the video. So this is the video which I took with my iPhone. It's 10 seconds with the default settings for a video. So the main object here is basically a bike. But I thought this was challenging because of the shadows. I wasn't sure about how Nerf will react about the shadows here. So it was interesting problem. I converted the video to MP4. The default recording from iPhone was .mov. So I converted to MP4. It's just one line, and using the FFmpeg command. So I copied it over to the Lightning AI, and I copied this whole studio from here. So the first thing is, let's prepare a folder for the images. We want to cut the video into images. So this will create a folder named bike with folder images underneath the main folder. So we'll use FFmpeg tool to cut the video into images. So we will have 2 frames per second, and it's a 10 seconds video. So in total, we will have 20 images. Let's run that command. Now let's check. Yes, we have 20 images. The next thing, we want to run VGG structure from motion using this command. So this command will run the demo under the VGG structure from motion, and it will store the results under bike folder, and it will allow us to visualize the output. So let's run it. So it finished the reconstruction, and it saved the output as a call map style in output bike. So these are the .bin files for call map, for the camera positions, for the images, and for the 3D sparse points. So let's visualize the output. The output is over port 8097, So Lightning AI provided a web server plugin where you can enter the web port. So 1897. Let's open that. Now you can find the output under demo visual bike. It mainly captured the structures right, and the output and the cameras. And this is the track that I was walking over, and these are the camera positions, and this was the bike. You can see it captured some of the shadows over here, and the color information are correct. So overall, it's a good starting point for NeRF, provided by VGG structure for motion, and it was very easy to set up, as you can see, and the weights were very good. You can tell you from the output that we're getting. The call map might be good, but the call map dependency, the software dependencies, the tools, I found it very hard to install call map. I tried to install it on Google TPU, I tried to install it on Lightning AI, but I couldn't. Maybe the algorithm is good. I'm not judging the algorithm, but I'm judging the installation. The installation is so frustrating. I couldn't install it anywhere. But in VGG's structure for motion, you can see that we got the output just right away. So this is the output for the structure for motion, which will be a starting point to train the NeRF algorithm. Let's get back. One more thing that NeRF expects is this structure. So under bike, we need to have a sparse folder. Inside it, a 0 folder, which has the call map output. Also, it needs the images in original resolution, another folder for images with 50% of the resolution, images with 25% of the resolution, and finally, images with 12.5% of the resolution. This file structure needs to be present on Google TPU in order to train the NeRF algorithm. So let's prepare this file folder. Now we have these 3 files. We have the original images. Now we need to resize the images and store them into these 3 folders. I got the commands here using Image Magic tool. I got these commands from the multi-NeRF repository. So this script, they call it local map and resize. These are the commands to resize the images, to create the folders and resize the images. So let's run these. The dataset path is bike. We are setting the home directory. So we're saving this variable to be bike. Then we're going to copy these commands just to create the resized images. So these are the images. Next thing we're going to do is to install the zip tool and just zip everything, the images in original resolution and resize the resolution. We'll zip everything into one archive and download it to be ready to upload it into Google TPU. So this is the zip file that contains the all the images and the original resolution and resized images. We will go into download that. We will go into unzip it and include these 3 files. So I have this zip file ready on my machine. Here I already prepared everything. So this is the original images, and these are the output files from Colmap. So it has the same structure that is required by NeRF. Sparse images, images 2, images 4, and images 8. So now we're ready to train a NeRF. So let's get started. So here is the machine that I'll be working on. Let's start the terminal. So I think this is new in macOS because I haven't seen that before. I think I got it with the last update. But I find it very handy. It reminds me of Windows the resizing Windows. So now we want to upload this zip file into the TPU virtual machine. We can do that using the upload tool here. Just select the file and upload it. I already uploaded the file, so let's check if it's there. So this is the zip file. All other files are coming from the original paper, the Mip-NeRF 360. Let's check inside that file. So we have the same folder ordered as required by NeRF. So we have the Colmap, the structure from motion, and we have the resized images. So to run this, there are steps that you need to do to install Conda environment, to clone the multi-NeRF repository. I already skipped those because I already uploaded a video on how to train a Mip-NeRF 360. I'll link the video and the markdown file in the description below. So you need to do those steps before you train the Mip-NeRF 360. So let's activate the Conda environment. Let's get back to the main directory in multi-NeRF. Now here's the command to move the zip file into the NeRF data directory and to unzip it. For training, we need to set these variables. The scene, bike, the experiment 360. It means that we are running Mip-NeRF 360. And the data directory is this directory, and the checkpoint directory is here. So these are the variables. And here is the training script. We are saving the checkpoint every 25,000. So after running the training script, you can see that it started training. Here's the training loss, the PSNR, and the learning rate. And it will go all the way to 250,000 training steps. and each 25,000 time step, it will save that checkpoint. And from every checkpoint, you can render a video. But I have to interrupt the training because I already have the training results. I leave it to train for 6 hours, all the way to the final time step, 250,000 time steps. Here are snippets from the training output. This is the last step where it reached 45 pace an hour. If everything goes right, you will be able to find the results in this directory. So these are the checkpoints, and you can render a video from any checkpoint. But if you run the rendering script, it will detect the last checkpoint automatically, and it will render from that last checkpoint. So here, this is a very short video. I have to change it. So we will have 20 frames with 25 frames per second. This will be 8 seconds video, just like the one we just saw. This one here, 8 seconds video, and the 25 frames per second will make it smooth. So I'll save this command. So you can copy this command and just paste it to run the rendering script. And you will find the videos here in this file. So these are the videos. This is the color video, the one on the left. This is the mean depth video, the one on the right. The median depth video, I didn't download that. And the accuracy video. So these are the 4 videos, but the most important ones are the color and the Mip. So let's analyze the results. I took the video from the front, so you can see that it's very clear, but it's actually did a great job in doing the 360 rotation around the object. And the rendering of the shadows it just simulates the original video. You cannot, I bet you cannot tell the difference. And from the angles that I took, imagine if I took a 360 angles video, then it will be a crisp reconstruction. But I took the video from the front just to challenge the algorithm and see how it will react from the angles that I didn't include in the video. But the final rendering is so crisp, and the color information so accurate. And the crazy thing is that it did that from only 20 images. And the data set that they used in the paper, they used almost 200 images. The one with the vase and the one with the bike, they used 200 images. So they have crisp information. But for this experiment, I only used 20 images. I wasn't restricted by the NeRF algorithm. I was restricted by the structure from motion, because if I include more than 20 images, I will get out of memory error and the Lightning AI TPUs. So there you have it, your own NeRF on a custom dataset. Thanks guys for watching. If you enjoyed this video, please like and subscribe. You can find all the commands that I used in this video in the description below. I acknowledge the help of the researchers who published their GitHub repositories or who published the notebooks, and I couldn't do that without their help. And hopefully you can acknowledge them in your work as well. Thank you so much. Bye.